All right, in this section, we are going to extend our discussion of linear functions into talking about a system of linear functions, or commonly called a system of equations. Our goal is to solve a system of two linear equations by graphing, or given the graph of a system, classify it as consistent or independent. We have some other terms that we use to classify a system of equations. So first off, what is a system of equations? Well, a system of equations is basically a set of two or more equations in which what we want to find is where the graphs of those equations cross. In other words, is there a point in which I can find both variables, x and y, where they are the same for both of the equations. So for example, here I've got two equations, and one is a line and another is a line. What I'm looking for is where those two lines cross. Well, I could guess, like I did down here, and I can say, well, is minus 1 and 3, is that a solution? Is that the place where those two lines have a common point, or where they cross? Well, I can try it. I can plug numbers in. So 3 times whatever the y value is, minus the x value, is equal to 10. So 3 times 3 is 9, minus a negative 1, so that's plus 1. 9 plus 1 is equal to 10. Yes, this point is on that line. Now, if this point is also on this line, then this is the point where the two lines cross. Let's try it. X is a negative 1 is equal to a negative y is a 3 plus 2. So negative 3 plus 2, that's a negative 1. So negative 1 is equal to negative 1. That checks out. So this point is also along this line. So if it's along this line, and as long as these two lines aren't the same line, then I have two lines that cross somewhere, and I've succeeded in guessing what the solution to that system is. Of course, I knew what it was to begin with, and you typically don't guess them. Okay, so that's one way of solving a system of equations. Guessing, not the greatest. But again, like I said, we'll find some other places. You can use solving system of linear equations in lots of ways. Remember these old questions where you have something like I ate 1,500 calories today. If I ate twice as many calories at meals than I did for snacks, how many did I eat at meals and how many did I eat for snacks? A question like that where you have sort of like two sets of information, those kind of questions you can use a system of equations to help you solve. And you'll see a number in your textbook that are similar to that. Okay, if I would like to solve a system of equations graphically, here's what I could do. Just take each equation and graph it. And then once it's graphed, then look for the point at which those two things cross. So for example, this one here, I can't graph it as it sits, so I'm going to change it to y equals mx plus b form. Y equals, move the 2x over, it'll be a positive 2x plus 1. So my y-intercept is at a positive 1. Let's put 1 right there. And then my slope is 2 over 1. So I go up 2 and over 1. Up 2 and over 1. So my line looks something like that. That's for the first one. Let's try the next one. Again, we'll move the 3x over to the other side. So I'll get y equals minus 3x plus 1. Oh, interesting. They both have the same y-intercept. Okay, so this one, my y-intercept is the same spot, right there. But this time my slope is minus 3 and 1, so I go up 3, 1, 2, 3, and over 1 this way. Or I could go down 3, 1, 2, 3, and over 1 the other way. So there are my two lines. One line is here, and my other line, my other line is there. So the question says solve this system. Or in other words, I have two lines or two equations and I want to know where they cross. So in this case, these two linear equations, they cross right there at that point. So graphically, I can see that the solution to that equation is the point 0 and 1. That's the solution to this system. And if I wanted to put a 0 in everywhere I see an x and solve for y, plug a 0 in everywhere I see an x and solve for y, I'll see that this point is satisfied in both of those equations. Okay, let's try another way. Another thing you can do is you can pull out your graphing calculator, or on the PC there's a free program called WinPlot. On the Macintosh there's a program called Grapher. Let me fire Grapher up. Oh, here it is right here. Let me get rid of that equation. Hopefully I can. Hopefully you can see that. Let me make it a bit smaller. There. Okay, so there you can see that. This graph I don't. How do I get rid of that graph? I guess like that. Okay, so I'm going to type the first equation in. X minus y equals a negative 6. It's nice that you can type them in like that on Grapher on the Macintosh. WinPlot, not as easy. Anyway, we want to get another equation in there too. So y equals 2x plus, 7. Go. Uh-oh, I just changed the first one. I want a new equation. Oh, there we go. So let's type the first one in again. X minus y equals x minus y equals negative 6. Good. There we go right there. Okay, so when I look at this graph here that you can see, I've graphed both equations. Here they are. And it looks like they cross right there. So that point would be, what's this, 0.51, 0.52. Yeah, each of these are 0.5. So it looks like it's going over negative 1 and up to a positive 5. So just looking at the graph from either my graphing calculator or a computer-based graphing program, I can see that the intersection of the two lines happens at negative 1 and 5. Notice that, I won't put the graph on here, but I'll just put the solution, negative 1 and 5. Notice that when I'm looking at the graph, it's almost like a ballpark. Some of the tools, like your graphing calculator and others, can actually tell you where the two lines cross. And if you want to learn how to use those solving kind of techniques, you're welcome to do that. But graphically, I can get fairly close. And then what I could do is plug these numbers in. Plug a negative 1 in for x, a 5 in for y, and see if it solves it. Negative 1 minus 5 is negative 6. That checks out. Plug in a 5 in for this, equals 2 times a negative 1 plus 7. 2 times negative 1 is negative 2 plus 7, sure enough, gives you 5. So this point satisfies both equations. Therefore, that point is where those two lines crossed. Okay, so that's how you could do it with a graphing calculator or with a computer. Now, when we look at solutions to system of equations, ones we've looked at so far have always been these ones, where my two lines cross. And if I get an equation where both my lines cross, then we call that one solution, and we call the systems consistent, and we also call the equations independent. It's sort of a funny kind of definition, but in terms of definitions for systems, this is what we'd call them. They're consistent, they cross. And the equations aren't the same equation, so they are independent. Now, if I had a situation where the two lines actually came out to be the identical line, like not parallel like these, but the identical line right smack dab on the other, if it's right smack dab on the other, the equations would be the same. And in this case, there would be an infinite number of solutions because at every point along there, it's a solution because they are touching each other there. We still call the systems consistent because there's a solution, but in this case, we call the equations dependent, like each one of them sort of depends on the other one, but they're basically the same line. And finally, if I have two lines where the slopes are the same, but the y-intercepts are different, like these ones here, if the slopes are the same, these lines will never cross. And that's why the systems are called inconsistent, because they don't ever cross. And again, the equations, since they're not the same, are independent. So that's some definitions that we often use when we're talking about system of equations. Typically, these are the ones where we give you most of the questions, where the systems are consistent, the equations are different, they're independent. That's where we spend most of our time looking for that point where they cross. But keep in mind that I could give you some, or your instructor could give you some, where the lines are the exact same line, or they're parallel. In that case, we have different descriptions of the systems. Okay, so for a little bit of practice, we could try this one. We could take a look at these two equations here. Now, when I look at them, I'm looking and saying, you know, it looks like there's a factor of 3 in there, doesn't there? Let's just try and make them look like the normal equation, the y equals mx plus b, and just see what we come up with. So I have 3y is equal to positive 2x plus 6. We'll divide both sides or everything by 3, so I'll get 2/3 x plus 2. So that's for the first equation. So the slope is here, y-intercept is here. Now let's do the second one. We'll move the 6x over to the other side. It'll become negative 6x minus 18. Now we'll divide both sides by negative 9. So I'll get y equals negative 6x over negative 9. And negative 18 divided by negative 9 is a plus 2. What I'm concerned about, though, is right here. Let's simplify that. Negative divided by negative is positive. Simplify 6 over 9. That's 2/3 x plus 2. Notice that I have a 2/3 here and I have a 2/3 there, indicating that these lines are parallel to each other. But I also see that the y-intercepts are the exact same number. So when I look at these two equations, it's actually the same line. So if they're the same line, identical, slope and y-intercept the same, then we call those consistent and dependent. So these lines would be consistent and the equations would be dependent. Okay, there's some others here that you could practice on, but practice some from your textbook and just refer back to those definitions to help you out. Try some questions. If you have troubles, holler.